Hey guys, it's Ms. Marfleck here. We're moving on to our next lesson in our Algebra 2 review, and that's going to be working with logarithmic functions. This is going to wrap up our Algebra 2 review here in the Pre-Calc Honors course, and then after this we're moving on to limits. You'll be happy to know that you're not going to have an assessment on exponential and logs. You'll only have a classwork that you have to complete for the exponential and logs, and then we're going to move on to limits. In the limits, we'll see our very first test, and then that's when we'll really start to see the content start to build and build. Now, just to let you know, when you were in Algebra 2, you did go over logarithmic functions, and you spent about 4 or 5 weeks on it. That's how much time is, or maybe even 6 weeks. That's how much time, I spend with my students. That's how much time is in the curriculum. So, whatever Algebra 2 teacher you had, they definitely went over logarithms. So if you think about how you spent maybe a month on logs in Algebra 2, and we're going to go over the basics of logs in one day. So there really is tons of things that you could do at logs. We're not going to see them all. We're just going to kind of very quickly go through the basics of different types of problems. And the goal here is, maybe just to refresh your memory on one more function. So we spent a while on that functions packet, and then we did exponentials. So we're refreshing our memory on just one last function, and that's our log function. We're going to jump into some notes, and I do think the notes is a lot for today, so I will be uploading a copy of my notes, pretty much like I have been doing, so if you don't want to write anything down, that's okay. So with our log functions, we first have to start with just writing down our exponential function, and in the last video, we went over how our exponential function is written in the form y equals a, which is usually our stretch, b to the x is the important part. Our base is raised to an x. And then what we're going to see is that log and exponential functions, they're inverses of each other. And we know what an inverse now is because we worked with inverses of functions, and that means that you switch your x and y. So with our log function, we could take our exponential function and we could switch our x and y. So I have x here, then I have b to the y. This is a log function. It's just written in exponential form, which can be a little confusing. So we're going to jump into not a textbook definition, but my definition here. And we say if this statement is true, then we can write it in log form, and we read log base b of x is equal to y. I like to say with my Algebra 2 students, we scoop and loop around. So we start with the b, and we read b to the y is equal to x. Scoop and loop around, and then that's how we write it in exponential form. So once again, this is a log function, but it's exponential form of the log function. And this is a log function, and this is our logarithmic form. Now, usually in problems, we're given, something in logarithmic form, and then somewhere along the way, we have to convert to exponential form to kind of help us solve. We do have some additional conditions here, like our base can only be greater than 0, can't be negative, and our x can't be negative, and there's things like that in the more formal definition if you want to look it up. But this will serve our purposes for our video. And then just 2 more things we have to cover before we jump into some practice problems here. You should have seen at the Algebra 2 level your common log, and that is your log that's base 10, and that's what you see on your calculator. So whenever you have a base 10, log base 10 of x, you don't have to actually write the little 10. It's assumed when you don't see anything that it is base 10. We use base 10 so much that it's become so popular that it has its own notation here. So when you see log nothing x, it's assumed that that's base 10. So when you're doing your scoop and loop around, your b will be 10. And then you have one more other type of logarithm, which you probably only spent a week on in Algebra 2, and we're actually not going to cover much of today, but you should see it again, and that's your natural log, and that's your log base e. Now, e is just a number like 2.71. It's an irrational number like pi, and it goes on and on forever without any repetition. And we write, instead of writing log base e of x, once again, it's so popular, it's used so much in the sciences that it has its own notation, and that's our ln x. All right, so a quick refresher on that. We're going to start off these practice problems by converting between the 2 forms. So switching colors here, my directions are going to be convert, and I'm going to, instead of putting, my first set, convert to exponential form and then convert to logarithm form, I'm just going to put convert between exponential and log form, just to kind of save time and writing space. So if you're given a problem in exponential form, we write it in logarithmic form. And if you're given the problem in the logarithmic form, we're going to write it in exponential form. All right, and then here's going to be our first one here. And it is log base 4 of 256 is equal to 4. All right, so we read here 4 to the 4th power is equal to 256. 4 to the 4th power is equal to 256. So what... this is our final answer. This is it in exponential form, but what logs help us do is they help us solve for powers. So like if you had something like this, you know, log 4 of 256, it's 4 to what power is 256, and that would be 4. But here's our answer in logarithmic form. We're going to keep in exponential form, given the problem started in logarithmic form. We're going to take a look at another one here. And we're going to scoop and loop around, and we read 7 base 7 to the 0 power is equal to 1. So we have 7 to the 0 power is equal to 1. Take a look at number 3. Now we have things, you know, switched around a little bit, and we got that log base 10. So we read 10, and then our power's always on the other side of the equal sign. See, the y is the power, always on the other side of the equal sign. So we read 10 to the 2nd power is equal to 100. So to go in exponential form, we write that 10 to the 2nd power is equal to 100. Base 10, common log, exponents on the other side of the equal sign, and then what it's equal to is in here in the middle. All right, and then we're just going to do one more going between going from log to exponential, and then we're going to switch around and do exponential to log. And here's the last one here. -2 is equal to log base, oh, I'm off page. -2 is equal to log base 12 or 1 over 144. So we're not actually solving for anything, just converting between forms. And we read 12 to the -2 is equal to 144, and then that's 1 over 144. And then that's it for converting from log to exponential form. I do think it's a lot easier to go from log to exponential form because we do draw the arrows, and I think that helps a lot of my students. And now we're going to go the other way, and we're going to start off in exponential form, and we're going to convert to logs. All right, take a minute. If you have to keep looking back at the definition to, you know, maybe you're going at a way slower pace than I am, and that's fine. Go back to the definition. Okay, what's my b, what's my y, what's my x in this problem? And then I'm going to come over here, and our b is always a number being raised to a power, and that's going to be our base. So this is a log base 5 problem. And then our exponent is on the other side of the equal sign, and then what it's equal to is in the middle. And then you could scoop and loop again to check your work. Well, 5 to the 2nd power is equal to 25, and that's what this statement here says. 5 to the 2nd power is equal to 25. All right, taking a look at number 6, we're going to have 729 is equal to 3 to the 6th. Once again, our base is the number that is being raised to an exponent, so it's 3. And then 3 to the 6th power is equal to 729. And then, you know, you could, like I said, logs help us solve for exponents. So it's like saying 3 to what power is equal to 729, and that's equal to 6. And then use that scoop and loop around and double check, and your answer is correct. 2 more to go here. Number 7, we have, what do we have? 1/2 to the 3rd power is equal to 1 over 8. So we got some fractions here, but not to worry. Once again, our number that's being raised to the power is our base. So we have a base 1/2 problem. And then our power on the other side of the equal sign, which is our y from our definition, is 3. Then that's equal to 1 over 8. Notice how the base is a small subscript. It's written smaller a little bit below the x. And then just one more to really drive it home here. We have 10 to the -2 is equal to 0.01. So this is a base 10. All right, so I can just write log. I don't have to write the little 10 there. And that's equal to the -2 power. That's my exponent. And then I scoop and loop around to double check my work. All right, so if this was really confusing, just use a definition, okay? Make sure you have this down somewhere, or I will be posting the notes and just keep kind of coming back to this part. All right, so here we weren't actually solving for anything. We weren't evaluating anything. We were just converting from one form to the other. But now we're going to do some very simple evaluation, and I'm not going to spend a lot of time on this. There are so many different types of evaluating problems. I actually spent a day or two just on evaluating in my Algebra 2 class, but we're just going to go over the basics here. And let's say I want to evaluate something like log base 2 of 8, okay? Let's say you have this on a standardized test or on a placement test in college. You can't use calculator. Calculators don't have base 2 unless you got one of those fancy ones. But for the most part, you can't use a calculator, but you can evaluate this without a calculator. It's like asking, okay, 2 to what power is equal to 8? So to solve something like this, I go into exponential form. I write 2 to the y power is equal to 8. Now, I'm just writing y, okay, because in the definition we have y. If you want, you could put x, okay, it doesn't matter, any variable, but the goal is to solve now this exponential equation, and it'll be the answer to the log. These are equal. They're the same thing. They're just written in two different forms. So now when I solve here, we learned how to solve for exponents using the same base, and you could see that y is equal to 3 as we rewrite with the same base and then use that equality property there. Number 2, we're going to put here, let's say I want to evaluate log base 3 of 81, and I want to see what that was equal to. Well, let's go to that exponential form. That's like saying 3 to the what power is equal to 81. Well, I can rewrite 81 with base 3. That's 3 to the 4th, and then using that equality property, and then my final answer here is 4. And then this one I should have filled in here. Log base 2 of 8 is equal to 3. Log base 3 of 81 is equal to 4. And then number 3, log base 4 of 1 over 16. All right, this is where things get maybe a little bit trickier, but not to worry. We also solved exponential equations like this. First, rewriting that exponential form, 4 to the what power is equal to 1 over 16. Well, we need to get the same base on both sides, so let's rewrite that 16 with base 4. That's 4 squared. And then let's use those property of exponents to bring that base 4 up into the numerator, and that inverse property changes the sign of our exponent. And then now we have the same base, and we get here our final answer is -2. So log base 4 of 1 over 16 is equal to -2. And then I just have one more for you, and it's going to be a common log problem, 0.001. And the powers of 10 follow how many zeros it has. Like here, 10 to the 0 is just 1. 10 to the first power is 10. See, 1 0. 10 squared has 2 zeros. 10 to the third has 3 zeros, and so on. The negatives work the same exact way. Okay, -1 has 1 0. 10 to the -2 has 2 zeros after the decimal. 10 to the -3 has 3 zeros after the decimal, so you can follow those patterns there. All right, let's rewrite this in exponential form. I read 10 to what power is equal to 0.001. Well, let's rewrite 0.001 as a power of 10, and that's 10 to the -2, and then my final answer here would be -2. -2. All right, that's it for evaluating. I was kind of torn about graphing a log, and I decided not to do it. So if you have some time, look up graphing logarithms somewhere on Khan Academy. I think it'd be really nice for you to see it in comparison to an exponential function. But we're going to move on, and we're going to keep it going, not with the graphing, but with the algebra here, and we're going to take a look now at properties of logarithms. Now, there's not too many properties of logs. There's mainly 3. Some people say there's 4, but we're going to take a look at 3, and they're not that difficult because they do follow the same exact kind of properties that you've seen with exponents or exponential functions. All right, our product property for logarithms says if we have a log base b of 2 things that are multiplied, we can separate them. Instead of using multiplication, we can use addition. Okay, we can separate them with addition there. And then we see this kind of connection between multiplication and addition when we did the property of exponents. And then our quotient property is going to be very similar. Well, if I'm dividing 2 things with 1 log, I could split them up, and it is the same as subtracting with 2 logs. And then the last one here, our power property. If I have m to the n power, that power can come in front, and then we're left with this statement here. Now, the power property, I'd say, is probably the best. Maybe some people don't think that, but it's really a beautiful property because it helps in so many situations where you have a variable in the exponent spot. It can be very difficult to solve for a variable in the exponent spot. Usually we don't solve equations like that, and when we do, you might have to use logs. And what's really nice is that this log property gets, like, let's say you had to solve for n, it gets it out of the exponent spot. And then once it's not an exponent, you know kind of what algebra tools to use to solve it. So that's something to always keep in mind. If you're searching for a variable and you're trying to solve a variable in an exponent spot, try to get logs somewhere into your equation. That way you can use this power property. Now we're going to just show some basics with using these properties. There's mainly two things that we can do, and that's expand and condense. So we're first going to start off by expanding. Starting the numbering all over again, here we are, number 1, log base 5 of 7xy. All right, so I can see right off the bat that this 7x and y are joined together through multiplication, so this is an application of my product property, which allows me to take anything joined with multiplication and split them up. So I can split this up as log base 5, 7 plus, because the 7's being multiplied to the x, and the 7 and the x are being multiplied to the y, and then there is my equation fully expanded. So here's an example of our product property. You guessed it, now you're going to see an example of your quotient property. Let's say we have log base 6 of 25 minus log, oh no, I wrote the wrong problem, and I don't have whiteout. Okay, here we are. That's all right. My notes just won't be very, very beautiful, but that's okay. Here we are, log of x over 4. This is a log base 10 problem because you can't see the base there, so it's a common log. I could see they're joined with division, so I know that that's going to be my quotient property. So I could split with 1 log to division to 2 logs with subtraction, and this is going to be log x minus log 4. And then that's a very simple application of our quotient property. And then here's going to be our last one. This one's going to have, it's going to be a multi-step problem, not too much though. And we're going to see an application of our power property. So I'm trying to, I did it again. I did it again. I have these really sloppy notes that I write out before I do the videos, and I was not as organized this time, but I'm not starting this video over again. I'm 17 minutes in. I'm in it to win it. Here we are, number 3, log base 3x to the 4th. And now I don't feel bad that I told you guys that I will be giving you the notes because I'm not making you scribble out on your notes. So hopefully you're not writing right now. All right, expanding, I can see that the 3 and the x to the 4th are first joined with multiplication. I can't do power property yet because the 3 is not being raised to the 4th power. So if I brought the 4 to the front, it's like saying the 3 is raised to the 4th power, and it's not. So first, I'm going to split this up using that product property. And then that I've split this up using the product property, I can leave log base 3 of 3 if you want, or you can evaluate this. 3 to what power is 3? 3 to the first power is 3. So log base 3 of 3 is 1. And then I can expand this one just a little bit further by bringing that 4 to the front, and then there's a very simple application of our power property. And then this would be fully expanded. All right, after you see some expanding, the next thing that we can do with our properties is condense. Sometimes the directions for condense are written a little different. Sometimes people say collapse, or they say write as a single logarithm, which means you have to condense everything to 1 log, but they all mean the same thing. And then here we are, we're going to start off with we'll start with the numbering all over again, 1, and we have log base 5 of 4 plus log base 5 of 3. Okay, well I see 2 things separated with addition, so that means we can go to the multiplication with 1 log. Here is an application of our product property, and there it is, our final answer, log base 5 of 12. Now, if you could evaluate log base 5 of 12, in your head, then you can do that, but we can't. We would need a calculator or something for that one, so we're going to leave it like that. All right, now we're going to be condensing for number 2. I see subtraction with 2 logs, so we're going to go to division with 1 log. And then now 25 over 5 is equal to 5. 25 over 5 is equal to 5. So we have log base 6. This is log base 6 of 5. And then same thing like the last one, I can't evaluate that without a calculator, so we're just going to leave that as is. And then I got one more for you for condensing, and this one is a multi-step one. And my goal is to write as a single logarithm. Okay, well, I see that subtraction. So if you want, you could do quotient first, but usually we do power first. So I'm going to condense this by bringing those powers to be our exponents. And then now that I've condensed with power property, I see the subtraction with the 2 logs, so I can go ahead and I can switch to quotient property and go to 1 log with division. And then I can simplify x to the 5th over x squared, and that's going to be x to the 3rd using those property of exponents. And there's my final answer for expanding. All right, I have 2 more things to get through. We have 6 or 7 more problems, and then we'll be done. All right, the next thing we're going to take a look at is solving exponential equations. Now, in the last video, we did solve some exponential equations, but we solved it by writing the same base. So we're going to learn today, or refresh our memories on how to solve when you can't get the same base on both sides. And that's going to be an example like number 1 here. So let's say I have 2 to the x is equal to 3. Okay, well, I'm looking at 2 to the x and I'm looking at 3. There's no way I'm going to get 3 to be base 2 like we did in the last video. So we use a strategy, and the strategy is to apply logs on both sides. Now you have to keep your goal in mind. Your goal is to solve for that x. So my reasoning for applying log on both sides is, number 1, I'm not changing the value of this equation, because what I do to one side of the equal sign, I'm doing to the other. But most importantly, now that I have logs, I can use a power property. And like I was saying earlier, this is super useful to get that power out of its exponent spot. So here's an application of my power property. And then now that that x is out of the exponent spot, I can actually solve for it by dividing by log 2. And then since these are base 10, you can definitely plug this in on the calculator. You could either leave your answer like this or get that decimal approximation 1.58. All right, so once again, for solving exponential equations where you can't get the same base on both sides, the strategy is to take logs on both sides. Like in number 2 here, there's no way 66 is going to be a base 9 or base 3, so we're going to take log on both sides. Now that we have the logs, we can bring the power to the front. And we're doing this next example because we're really illustrating that the entire power goes to the front. Not just the x, but the 2x is the power. And then I have still that log of 9 and then log base 10 of 66. And then now I'm solving for x, and here's an interesting rule of algebra that I always get questions on, and I don't know why, but yes, divide by 2 and log base 9 at the same time. Or you can divide by log base 9 and then by 2, it'll be the same answer. And then you can plug this in on the calculator, and you should get about 0.95. All right, we got one more example problem for solving exponential equations, and that's going to be number 3. And we have 2 to the x plus 3 is equal to 515. All right, just like solving the exponential equation problems previously, or, you know, even when you're working with square root, anything, absolute value, we saw it with the absolute value inequalities, maybe like 2 or 3 lessons ago, you always have to isolate. So I have to isolate this exponential factor, which means I'm going to be first subtracting 3 from both sides. And then that's going to give me 512 on the other side. Now that my exponential factor is isolated, then I can start by using that strategy of taking log on both sides with the intention of getting that exponent out of the exponent spot by using my power property. And then here's another good practice problem to really illustrate that entire power is getting out of the exponent spot. First, I have to remember my order of operations. When I'm solving for x, we do them in reverse, which means that I'm going to be first dividing by that log base 2. And then once I've divided by that log base 2, I'm going to take that whole answer and I'm going to subtract 3. So we're going to have log 512, log 2, and we're going to subtract 3. And if you do that in the calculator, you should get out 6. Exactly, you should get out 6 exactly. All right, so basically with our solving exponential equations where you can't get the base on both sides, the same base, our strategy is to apply logs and then use the power property. All right, the last thing we're going to go over is just a few examples of solving log equations, and then we are done. And here we are, solve log equations. We're taking a look at this first one here, and we have number 1. Now, surprisingly, solving log equations is very similar to evaluating in the sense that most of the time you can scoop and loop around to solve. So we go from log to exponential form, and this is 4 squared is equal to x plus 3. And then now you got rid of the log because you wrote it in exponential form, so now you can just solve for x. You have 16 on this side, and then lastly you have x is equal to 13. And then you just have to double check when you plug your x in here that this answer is always positive. Remember at the beginning of the video, I said I didn't give you the whole kind of definition from the pre-calc book, but I did say that this answer in here, that x always has to be positive. All right, so this is an example where you can just scoop and loop around, rewrite in exponential form, and then solve for x. And then here, number 2, we have 3x plus 1 is equal to 5. And then this is a common log problem. So when I scoop and loop around to rewrite in exponential form, this reads 10 to the 5th is equal to 3x plus 1. And then 10 to the 5th is a 1 with 5 zeros. And then no need for a calculator. 100,000 minus 1 is 999,999. Then divide that by 3, that's 33,333. And then there is my final answer for x. And then double checking, I plug it in, I'm going to get a positive answer. 2 more to go, stay alive, and here we are, number 3. All right, so the last 2 examples were where you were able to just kind of scoop and loop around to solve. Sometimes you have to condense first before you can scoop and loop. So keep in mind, when you scoop and loop, you're writing it in exponential form. You can only have one log. So first condense to a single log, and then write it in exponential form. So let's condense to a single log by first using that power property and getting that 2 to come and be an exponent. And then now I have 2 separate logs joined with addition, which means I can combine them to multiplication. Now it's a common log problem like number 2, where I can rewrite in exponential form, and then we're just solving for x. This is 100. Then when I divide by 4, I get 25. And then I can take the plus or minus the square root. Remember, when the radical's already there, it's assumed it's positive. But when you apply a radical, you take positive and negative. However, when you get to this part here, this is 2 solutions, x is equal to 5, and x is equal to negative 5. However, when I go back and I check my original problem, I can't have a negative number here. So this is what we call our extraneous solution, and this is our solution. An extraneous solution is an extra solution that arises kind of as a consequence for the algebraic steps that you are doing, but it is not an answer to the original problem. And then here's our last one, and we're going to make it just in time. Under 30 minutes was the goal today. And we have log base 7 of 3x plus 2, and that is equal to log base 7 of 2x plus 5. And then this is our last type of log equation we're going to go over. Now, this is very similar to the sense that we were able to get the same base on both sides of the exponential and get rid of them for equality. That's the same thing here. I have the same base on both sides. I can get rid of them using that equality property. And then now I just have 3x plus 2 is equal to 2x plus 5. And then I'm able to solve, and x is equal to 3. All right, guys, so I know I went through a lot of different types of problems in this video. I basically covered, what you spent a month on in Algebra 2 in one day. But keep in mind, you're not going to have an assessment on this content. You will have a classwork, and the classwork will be basic problems, very similar to kind of what we've done in this video together. If you're a little bit more curious and you really want to prepare yourself for whatever math class you're taking next year, please, spend some extra time, go on Khan Academy and do some extra things with logs, such as graph graphing, some things that we couldn't cover together. I'm really looking forward to our next video because we are starting limits together, and that's something to be, I think, excited about because that's the last thing that we're doing before the end of the year, and I can feel the end of the year coming, but that's when it really becomes crunch time because we're hitting the calculus. So this is the end of our Algebra 2 review here. If you felt like the past 2 or 3 weeks was very challenging, that maybe because you don't have a great foundation of Algebra 2 and you really should be doing some Khan Academy, maybe just download the app on your phone over the summer to prepare for next year. All right, email me if you have any questions and get to that assignment.